Hello and welcome to the Deep Sea Podcast, a punk take on a science podcast about everything deep sea. I'm Dr. Tom Linley, curator of fishes at the National Museum of New Zealand, Te Papa Tongawerra, and with me is Professor Alan Jamieson, director of the Deep Sea Research Centre at the University of Western Australia and scientist for Inkfish. A little bit of a pivot on this one. The show is now about building raised flower beds. How are your raised flower beds, Alan?
Very good, looking voluptuous.
Were those reclaimed railroad sleepers? You've got some very rustic looking wood in yours.
No, the very large chunks of wood. The first one was reclaimed from another part of the garden from a previous owner, which were dismantled and rebuilt into a far superior product. And the second one at the back, they were bought new.
I have dabbled. I built a prototype under review, whether it will hold the soil.
The trick to a good flower bed, Tom, it's got to be solid. Did you put plastic lining on the inside as well?
Oh, of course. Mainly because our soil is full of lead.
Ah, right.
We're growing food in raised beds. So yeah, after 120 years of lead paint off the lovely rickety house that I foolishly bought, my soil is poison.
It's right in small doses, I'm sure. Small doses over a long period of time is fine, right?
Yeah. Continual heavy metal poisoning is pretty good. So yeah, that's what the show's about now.
Yes, if anybody wants me to come and design them a raised flower bed and come round and fit it, quite cheap. Big Al's flower beds.
I'll find some way of putting them in the show notes. I might put them on the social media, but you'll see our flower beds. Other than flower beds, what have you been up to? You said you had a big deep sea story for me and you wouldn't talk about it.
I do have a deep sea story. This is
recording.
genuinely a deep sea story. So I'm back in Edinburgh again because I'm trying to get my jet lag quota for every month. And so I've just done another good solid 7 days of waking up at 4 a.m. I had some visitors. On last Friday, I was visited by Mr. Andrew Henderson of the good ship Pressure Drop / Dagon. He's a sub-pilot and engineer, an all-round good chap. He came over from Barra in Scotland, and also joined by Jenny Wainwright, who's my PhD student in Perth, who's from Newcastle, England, and happened to be back in Newcastle. So the three of us went to Edinburgh for a bit of an afternoon, but decided it was a bit early, so we should go do something wholesome instead. I decided to take them to Dean Cemetery in Edinburgh because I happen to know that there are a load of interesting deep sea people buried there.
Wow.
And so we thought we'd go and see if we can find their graves. So there's some absolute massive deep sea legends all buried in the same the cemetery's broken down into 3 bits, but the oldest bit is actually really interesting. There's loads of big names in there. So we're wandering around for hours. But the first one we found was John Buchanan. So John Buchanan was a Scottish guy. He was the chemist on the Challenger expedition. He was probably one of the first marine chemists. He was an Arctic explorer and all this kind of stuff. So we found his grave, and I was like, oh, that's cool. Pay homage to the legends John Buchanan. And then we found Edward Forbes. We all know that Forbes' azoic hypothesis. So he's there. He's got a nice big obelix next to his mate called Good Sir, who was a big cheese in cell biology. The two of them were mates, so they got buried next to each other with identical obelisks. So it was quite cool to sort of stood there next to Edward Forbes himself. Yeah, he's got a nice plot. But then the big one we wanted to find is Sir John Murray. So he was on the Challenger expedition as well. He was technically he was Canadian, but of Scottish parents. But I think he was the guy who basically invented bathymetry. He basically went, there's the whole landscape under here. You know that, right?
You know, it gets shallow in the middle.
Yeah, stuff like that. So anyway, so John Murray's one of the biggest cheeses, one of the godfathers of deep sea science. And God, trying to find his grave was incredible because we've got pictures of these things. You can see them on Wikipedia and stuff like that. A picture of the grave. And you're like, we're looking for this one. This one here is in this bit. We're walking around for hours and it'd fallen over. Jenny found it in the end. We found it, but it was the only one in thousands and thousands of graves in Dean Cemetery which had actually just toppled over. And it must have been recently because none of the photographs online have been toppled over. But we found it. So we should have a campaign with the podcast to get Dean Cemetery to raise his grave again because he's the godfather of deep sea science.
To get him popped up.
Unfortunately, his grave wasn't set very deep into the ground and it's just went buff and it's lying on its back. I can send you a picture for the show notes if you want to see it. Yeah. But that's why it took us about 2 hours to find the damn thing because it wasn't. We know what it looks like standing up, but we weren't expecting it to be lying on its back. So, but yeah, there's a whole bunch of interesting people. It was a nice thing. It was an interesting thing to go pay homage to all these big greats in the business.
That's an amazing story.
Good fun day out.
How did you do the research on that? Did you just know that they were there?
I can't remember. It was ages ago. I was writing something else about one of them, and I noticed it is buried in Edinburgh. I thought that's weird. Next time I'm back, I should go check that out. And I saw the 19th cemetery, and I was like, I know where that is. Actually, that's kind of weird. There's a Wikipedia page for the cemetery, and it's got a list of notable people buried there, and you go through it and you're like, my word, you know, in the 1800s, like every big name in anatomy and philosophy and arts and science, and so many people you'll recognize the name. And then there's a whole bunch of people in there from the Franklin expeditions and stuff like that. And then suddenly you start seeing repeated sort of person from the Challenger, and then you look at Edward Forbes. I didn't think he was even Scottish, but yeah, there's quite an impressive. I think that cemetery was for the high society at the time. It wasn't necessarily for the commoners, so it's quite an elite bunch
Yeah,
of
it's not an accurate sample,
people,
but what a
so-
sample to have.
Yeah, and they're all like Royal Society or they're fellows of the Royal Society of Edinburgh and all these types. Really cool.
Oh, that is a good story. I wasn't ready for that. That was a good story.
Yeah, there you go.
Oh,
That's what I did on Friday. And then we all went to the
and
pub.
then we all went to the pub, as all the stories end. Just want to say a huge thank you to our patrons who continue to support us and make the show happen. And this month, we would like to thank C. Wright. Thank you. We couldn't do this without you. Welcome aboard. And when you join the Patreon, you also get access to the Discord. And I'll start including little updates from the Discord as well, which has been rather busy this month. So Alicella gigantica, the supergiant amphipod, has been having a good month. The wiki page was updated last month by Sean, and Alan, your team did that one. That was one of your big wiki pushes, wasn't it, to put that one on there? Sean did some updates, and it was hosted on the main Wikipedia page as a featured article, and it was also featured on Radio New Zealand's Critter of the Week. So it's been enjoying a little bit of fame recently. There's been chats about horseshoe crabs. There's been fun blacklight pics of fluorescent nematode parasites and light organs photophores from the subantarctic squid that Cat's Squidmus AUT Squid Squad have been processing. Some of them look like modern art, actually. Some of the dissected squid with glowing bits and parasites, and it's gross, but it's quite pretty. There have been a few photos from boat trips, including the world's oldest sailing ship, the SS, oh, how do you say that? Solandet.
I have no idea, but well done. That sounded suitably Scandinavian.
Yeah, and visits to an Eocene epoch fossil dig sites. Actually, a few people were out digging for fossils. That was quite fun. And then lots of art and bizarre board games and bizarre computer games, including Shark Dentist, and I will say this as politely as I can, genital jousting, which was pulled very quickly from YouTube. So lots going on there if you want to join the community. On to some deep sea news. The first one, I'm going to let you do because you've got your name on it. So who better to ask? Rethinking the deep sea, the boundary of what we consider deep sea.
This came from the podcast. The original sort of half draft of this was something that I had a rant about on the podcast because I thought it was worth doing. And there's a journal section in IC's Journal of Marine Science. It's called Food for Thought. So you can just put down interesting ideas, and that's what they're for. They're not saying this is. It's kind of like an opinion piece, I guess. But Food for Thought is it's not an opinion. It is a concept of which we're raising it. Has anyone ever thought about this? Really, stuff that you take for granted that maybe you don't know you're taking for granted. And that's where we put the fear and loathing one as well. It was like, and the idea was to think a little bit about the language you use when you talk about deep sea. This one was trying to rethink what the boundary for the deep sea really is and whether 200 meters means anything at all. And the more we get into it, the more we realize 200 meters means nothing at all, really. One of the biggest things was it really only applies to going back to the likes of Challenger expedition and stuff like that, and the John Murrays of this world. It made a lot of sense when you were leaving Western Europe to go out to North Atlantic because you have this huge big slab of 200 meters. The water quality is such that light probably doesn't penetrate much more than 200 meters in that area, but it doesn't really apply to anywhere else in the world. Continental shelves around Antarctica or around the Pacific, that either in the Antarctic case, they're much, much deeper. In the case of the Pacific, there isn't really much of a continental shelf at all. So the 200 meter thing just doesn't work. So I wrote it as a bit of a rant, and I brought some others in with me to make sure I wasn't going too far down personal opinions on these things. And we submitted it, and it came back and forward multiple times, and it caused no end of grief.
That's how you know you're onto something, though.
I must admit, I'm not really happy with the one that was finally published.
Okay.
I must admit, I thought it wasn't what I wanted it to be. But that's because you have to make lots of compromises. In scientific literature, you're kind of constrained a lot in what you can get away with, I suppose. Not get away with, that's not the right word for it, but there's things the ideas you want to get out there, but everyone knows are true, but you don't necessarily have anything to back it up. So then you're in that grey area of, it's a difficult one. It was very hard-earned, I must admit. It took a long time to get it out. And my original idea was that I don't think 200 meters means anything, which I think if you read the paper, you'll find that 200 meters doesn't mean anything. It's just a completely arbitrary, made-up thing, and it does a lot of damage, I think. But I think if you really do want to define a deep sea, it should be 1,000 meters. But I wasn't allowed to say that in the paper. That got taken out.
There is a place where you can say that.
Well, I've already said it in the podcast, but I think 1,000 meters.
Yeah, we have on the original rant, and it makes sense. It's
Anything the top 1,000 meters is easy, right? It's just easy. It's not deep anymore. So the whole point of questioning the deep sea is the word deep is very subjective. Before scuba diving, about 5 or 10 meters would be considered to be deep. But once you get a scuba tank on, 50 meters is deep. Once you get various other things, when you start fishing deeper, it's only deep when it becomes difficult. And I think we're at the point now where just fishing and drilling and mining and reshaping the seafloor, drinking seawater and, regular eating food from the top 1,000 meters. It doesn't feel that deep anymore. It doesn't feel that out of touch in the slightest.
It also shouldn't be set by people. It shouldn't be based on us and our limitations. It should be about the environment.
Well, I also had a big section in there originally about how it compares to high altitude. And high altitude biozones, if you like, are defined by the way in which they perturb human health.
Oh.
So there's a certain limit where you cannot survive there. There's a certain limit where you can if you're genetically predispositioned to it. And there's another one where you can for a period of time. And then there's another one where you're not good. There are measurable delimiters to these things based on human survival. But then you can't really apply that underwater because you just drown in the top foot.
Yeah, what's the timescale? Dead, 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 dead.
If it is even important, if it's even important at all to do this, maybe they shouldn't have any line in the sand at all, because I think that a lot of the stuff we talked about in the podcast is that you can talk about marine science and everyone's happy, and as soon as you prefix it with deep sea, it's like, well, it's not my problem anymore.
Yeah.
And the problem is that line. So if you made that line a bit bigger, well, the majority of harm we're probably doing in the deep sea probably is in the top 1,000 meters and it's percolating down. So maybe if you change the boundary to make it deeper, change people's attitude to what is deep and what is shallow, it might be a good thing. Anyway, the whole point is food for thought article. You read it, whether you disagree with it or not, doesn't matter. The whole point is it gets you thinking about it. And next time you write the word 200 meters, you can say, does this actually apply here? Or is this just a figure that I've always been told I should write here? And that's the point of these things. If I ever publish my book of interesting thoughts, I'll put the original version in the director's cut.
It's got to be important when that book comes out. You've got to be ready to retire though. It's the last thing you publish.
Yeah. Anyway, I hope people enjoy it. We did do a lot of interesting little anecdotes and interesting things along the way. So
it's definitely worth a read. If you're new to the deep sea science, if this is the episode you've landed on, jump into that for your wider reading, because it's so much of it comes from our end and our concepts and our boundaries, and it should be led by the environment. Yeah. That's what you're studying.
The problem is with the review process, science generally is very black and white. Is that you agree with it or you don't agree with it. Some of the more interesting papers, well, we've talked about these in the podcast, like there was the one from the geology guy who had a real issue about people naming underwater features for stupid stuff. The jellyfish guy who was talking about the lack of natural history in the age of molecular science, stuff like that. Now, there's elements of both of those things that I agree with and I don't agree with, but I love them as papers. I love the fact it's just a guy, he's obviously, the backstory is he's probably just like, right, that's it, I've had enough.
It's the last
Somebody get me a typewriter because I'm putting this down on paper now.
The best papers are written in spite.
I think so. I think because it's unusual to get something quite passionate through scientific literature when it's written quite often very sterile, but between the lines you can tell that this is a largely frustrated person who's like, can we stop doing this? Or at least if we're going to do it, can you all just take a moment to think about what it is you're doing?
And even if you disagree with it, you should be able to still peer review it. You can disagree with it, but say this has been presented well. There's not a flaw with the paper. I don't personally agree, but it's not incorrect.
Yeah.
Especially an opinion piece. You can't tell someone their opinion is wrong. Although we're really into that right now, apparently. You can tell people their opinion is wrong.
Oh, this is it. I think this is probably the last paper I'll ever write of that kind of ilk.
Until the book, and then you go live in a cave.
The book.
If he disappears, then we need to go and lift up that tombstone in Edinburgh, and there'll be a tunnel under it. And that's where he is, cuddled up. That's where he goes. Comes out at night. On the back of last month's episode on mesophotic reefs and mesophotic communities, NOAA have released a really nice, it's what's called a story map, a sort of flow of information, very sort of breezy and easy to take in. And it's on their mesophotic research in the Gulf of Mexico following the Deepwater Horizon spill. So we'll put a link in the show notes there and you can sort of explore that topic. Lots of nice images there. And another one is actually a research team that got in touch with us hunting the wrecks in the Great Lakes. So there's a project to chart the wrecks of Lake Ontario in the US, but who better to explain than actually the team that did it? So I'll hand over to them to talk about their research.
Hi, everybody. This is Jason Fay, the Associate Director of NOAA's Ocean Exploration Cooperative Institute. I was lucky enough to participate in an expedition in late May on Lake Ontario to look at shipwrecks in the new Lake Ontario National Marine Sanctuary. This project was exceptional in that some of the shipwrecks had been previously identified by the local shipwreck hunting community. Others were blips in sonar data that had not yet been imaged. And a few we actually surveyed and found our own. I was lucky enough on this expedition to be joined by a group of students and researchers from the university and also some phenomenal NOAA colleagues that helped serve as chief scientist and really provide the historical context of a lot of the wrecks that we were discovering. A key piece of technology during the expedition was a new ROV at the University of Rhode Island that we're calling Rhodey. The ROV was made by JM Robotics. It was unique in that it integrated a new stereo camera system from Voyis, which allowed us to capture over 750,000 images over the course of the expedition that we'll use to generate 3D photorealistic models of the shipwrecks throughout the summer and into the fall. These models will be used by NOAA's maritime archaeologists to understand the baseline kind of condition as we saw them of the wrecks and help identify some of the wrecks that currently don't have names associated with them, but also they're going to be shared with the public. For more information on the expedition, please check out the Lake Ontario National Marine Sanctuary Facebook page or uri.edu.
And there'll be links to their work in the show notes.
So there's a deep sea limpet named after a one-piece character, and it's a limpet that was found on hard volcanic rock at a depth of almost 6 kilometers deep. The deepest known habitat for any true limpet, which is a subclass of Patelogastropoda. It's collected using the Japanese Shinkai 6500 sub, the first of its genus to be observed and collected from its habitat without a dredge net. So they called it Bathylepeta Waratsumi after the character Large Monk. And I'm supposed to know what that means. Large Monk Waratsumi from the One Piece, which is an anime of some kind, as well as Waratsumi, the god of the sea in Japanese mythology. So in One Piece, Large Monk Waratsumi is a giant fish man and a member of the Sun Pirates. So if that means anything to you whatsoever, then congratulations, you now have a limpet.
Chalk that up as pirate booty.
Yeah.
I can't get into One Piece. It's got like 500 episodes. I have not got that level of commitment.
I think I just skipped past it one night and I was extremely bored. I thought, no.
Microbial life on Earth as a model for the cosmos. Researchers led by James Holden, a microbiologist at the University of Massachusetts, Amherst, is using Earth's deep sea microbes to model what life could look like on Jupiter's moon Europa. So recently hired by NASA, Holden is focusing his research on the Earth's deep-sea volcanic hydrothermal vent environments that may closely resemble Europa's subsurface conditions. It's believed that Europa may have a molten core and therefore may have hydrothermal vents under the ice, and these vents would release minerals and gases into the water, potentially providing an energy source for life in the absence of any light.
I can't help but notice on your show notes here, Tom, it says Alan appeared on the podcast too. What does that refer to?
On a podcast too. You were on a podcast. I posted a link in the Discord. Discover Magazine. Oh. Did you record it a while back?
I think that was a few weeks ago. I don't know. It was a busy day.
We only do this every month.
No, I don't think I did actually.
You did great.
Thanks. I don't remember anything what I spoke about, but
you did it in a fugue state.
I barely remember even.
Definitely go and listen to that because Alan can't remember it.
Oh, it's one of those things you got like 10 million things to do in a day. One of which is to sit down for half an hour and just talk deep sea to someone on Teams, and then as soon as it's finished, you're doing something else, and someone's knocking on the door, and someone's asking for this, and somebody wants this, and I have no idea. I better listen to it in case it's potentially damaging.
It was good. It was good. So you were on that one.
That's nice.
Yeah. Moku Art Studio and Sustainable Ocean Alliance have paired up for a series of chats that feature scientists and artists in an open conversation Zoom meeting. And the first of these free chats was hosted on July 17th and had Paola Santiago Padua, a PhD student studying deep sea and Antarctic methane seep food webs, and our very own Megan Jones, an artist and author who draws inspiration from the deep sea and helps out with it as well. This fun, informal chat lasted about an hour, had loads of great input from the audience, and was recorded for your viewing pleasure on YouTube. Future talks are planned, and you can find out more by following @Moku Art on Instagram. Links to this deep sea reef chat is included in the notes, so you can go and have a listen after this one.
Also, scientists find a bioplastic that vanishes 80% even in extreme deep sea conditions. So a Japanese research team have demonstrated a novel microbial polyester called here we go, D-lactate co-3-hydroxybutyrate.
I think I had that once. I had to take drops.
Yeah, that affectionately known as LAHB, can lose over 80% of its mass over 13 months at a depth of 855 meters. This microbial lactate-based polyester that actively undergoes biodegradation and complete mineralization, even on the deep sea floor, gives hope for the future of sustainable, biodegradable plastics. There you go. I think you need a better name than polydilactate co-3 hydroxybutyrate.
It'll get a branding, won't it?
Call it like Deep Sea Dave.
Deep Sea
Something like
Dave.
Yeah.
Deep Sea Dave, the healthy plastic.
Yeah.
Funny you should mention mineralization.
Is this to do with the lead in your garden, in your flower bed? Is this what inspired this next interview, was the fact that you've got a slow
I'm highly mineralized.
precipitation of lead into your nasty little flower bed?
As it's clogging my neurons because I ate my own strawberries. Well, mineralization, processes in the deep sea. The Earth is a closed system. Everything needs to be recycled. Living things like to tangle up the Earth's elements in all sorts of complicated molecules that prove really difficult to break down. Something is needed to get them back to their original form, a process called remineralization. Remineralization. In this episode, we're going to talk small about some really big processes that take place in the deep ocean and keep our planet in balance and ticking over. I'm lucky to be joined by Professor Ronnie N Glud, leading biochemist and the director of the Danish Center for Hadal Research, Hadal, at the University of Southern Denmark, with a cross appointment at the Tokyo University of Marine Science and Technology. Ronnie's work focuses on microbial activity and diversity, as well as the biochemical function and importance of hadal systems, the deepest part of the ocean. Thanks for coming on to chat, Ronnie.
Thanks for having me.
We've sailed with each other a few times. We've compared landers, very different devices. Your systems are very different from ours. So we'll definitely get onto the tech as well for a little bit later. But I think before we get going, we need to sort of set the scene. So what is remineralization? How does that fit into our planet's processes?
Let's maybe move back and a step further back. So just the deep sea, the sheer size of the deep sea is immense. It's huge. The deep sea covers more than 65% of the planet. And processes in the deep sea are fundamental for the element cycling on the planet, for the biodiversity, for energy, for climate change. And therefore, we need to understand processes in the deep ocean to understand how the Earth functions and how the Earth's systems respond to, for instance, climate changes or interrelate to climate changes. And one of the important things that we want to understudy in the deep sea is how important processes in the sediments, covering more than 60 to 70% of the planet, the processes in these sediments and how important they are for the carbon mineralization. And when I say carbon mineralization, what I mean is that a lot of organic material is either washed out from the continents into the oceans, or it's produced in the surface oceans, but ultimately a fraction of that end up in the sediments at the seabed as such. And the fate of that material is very important for understanding the carbon cycling in the deep ocean. The organic material produced either in the surface ocean or washed off the continent is settling in the deep ocean, and there it sustains deep sea life because it's a food package. The organisms down there are living on that. And to the extent the mineralization is happening, that means all the organic material is degraded into its original constituents. They are producing CO2 and nutrients and so on that can continue in the element cyclings of the ocean. But to the extent that doesn't happen, it's actually buried as an archive in the deep sea sediments. And the balance between how much is actually buried versus how much that's mineralized is actually what is regulating how much CO2 is in the deep ocean, and is also on geological timescale regulating how much oxygen we have on the planet. So the mineralization processes in the sediments of the deep ocean are fundamental, for instance, for the whole redox level on the planet, meaning how much oxygen do we have in the oceans and in the atmosphere, and therefore a fundamental premise for rest of the life on the planet.
It's tiny things at an enormous scale. There's lots of really fine, and I'm sure we'll get into it, but when we've talked before, you've shown me at the like sub-centimeter scale a different diversity and a different habitat, and then that seems so tiny, so insignificant, but it's so much of the planet. This is a huge driver for the stability of our planet, but it's tiny things in mud.
Yeah. It's really the bacteria in the sediments that's doing the trick. The bacteria is a vast amount of biomass. There's so many bacteria on the planet, it's incomprehensible. There's 10 to the 30th, means 1 and 30 zeros after that, of bacteria on the planet. And that's so many It's more than there are stars in the universe. If we put them shoulder to shoulder from the planet and up to the nearest sun, not our sun in our own solar system, but the next sun, it will reach up there to several million times one long row of organisms. And when they respire, when they do metabolism, when they do mineralization, it affects the household of elements on the planet. And that's really what's driving the element cyclings on the planet. And that's sort of fascinating, I think, that these teeny tiny organisms are actually the key drivers for some of the most important cycling of bioelements that makes up of the rest of the biomass, including us on the planet.
Yeah, we're quite a rarity, really, multicellular eukaryotes. We're not much in the big scheme of things, although we do like to make a mess. So within that mechanism, what really captured you about the Hadal trenches? They're only 1% to 2% of the planet's surface, but they're pretty unique in this backdrop, aren't they?
They are. So generally, when we go deeper and deeper in the ocean, the biological activity declines. And that's simply because less organic material is making it to the deep ocean. But when we go into the trenches, we had a presumption that maybe material do get focused. So the material that do make it down to the deepest part of the ocean is focused in the trenches. So maybe the biological activity would increase again when we went into the trenches. That was indeed the case. So we discovered that there was a lot of active microbes in the deep trenches, and that quite took us by surprise that it was so much the higher activity in the trenches than it is in the rest of the deep sea. And that's simply because food, organic material, is focused along these trench axes.
We've talked before about the sort of funneling effect of the trench, and it being seismically active as well usually sort of shakes sediment down into it. And then at the bottom of the axis, there's this really fine sort of soupy sediment, which at first seems pretty barren. It looks like another planet. But if you put some bait down, things start emerging from it. And beyond what we can see, we know from you that there's a huge amount going on within those sediments. It's hard to study these really fragile organisms because it seems like you do as much as look at them and their proportions change. So you had to go to them, didn't you? You've designed some very cool gear over the years.
Yeah. So obviously we cannot just take a lump of sediment up to the ship and start studying and not expecting it to be changed by the recovery process. Pressure is changing, temperature is changing, and we are disturbing this sediment if we take it up on ship and start studying. And that's what people have been doing in many years. But what we have realized is that you really need to go down and measure the processes directly at the seabed if you want to get trustworthy results. So we have developed various lander systems, as we talked about initially, that can measure these processes. And we have a range of different lander systems. One of the most successful one is one where we have small sensors, oxygen sensors, that can actually measure the oxygen distribution at very, very high resolution across the sediment-water interface. And from that, we can map the oxygen distribution in the sediment. And from that, we can again calculate how much oxygen are the bacteria in the sediment using. And that's a fundamental measure of how much organic material is mineralized in these sediments. But we also have other types of landers that can do different other experiments. We can inject different types of organic material. We can measure other processes that oxygen consumption. And it's fundamental to do these measurements down at the seabed at the right pressure, at the right temperature, without disturbing the sediment to get real correct measures and data and answers.
I was staggered by the resolution, by the scale of these differences. You know, something that just looks to me like a couple of centimeters of mud. You found multiple distinct communities and multiple distinct sort of chemical processes taking place, right down into the millimeter sort of scale, weren't you? What are the sort of main structures of the Hadal ooze? Because there's a lot more going on there than I gave credit.
Yeah. If we start first at the very, very shallow ocean, what we have is, we all know when we go out and for a swim and near the shore, we see that these sediments are very loaded with organic material. And when we sort of study the microbial communities and the processes in those, we have a steep gradient of processes. Oxygen is consumed in the upper millimeters, then nitrate is consumed, manganese, iron, sulfate, and other processes or other elements are being consumed as we move into the sediment on millimeter to centimeter scale. But when we move into the deep sea, there's so little organic material that makes it down there. So oxygen is sufficient to drive all of the mineralization processes. And there's actually a very low biodiversity in the general deep sea. But then when we go into the trenches, all of the processes we saw in the shallow ocean now start re-emerging because there's so much organic material in the trenches. So we again see these very fine resolution, vertical distribution of all of these processes, oxygen respiration, as we also are using, many bacteria using that to generate energy. And then comes all the other processes we have known from the shallow ocean. But now they occur at an extreme pressure and very low temperatures. So completely different communities we thought originally than what we find in the shallow waters.
Yeah, anyone who's sort of dug on a beach, especially a beach with plenty of nutrient load, will know how quickly that oxidized golden sand turns into a black sulfuric, rotten egg smelling mess. And it runs quite a lot deeper in the trenches. Or actually, you've found huge variability, haven't you? You've found even at the really small scale, no 2 teaspoons are the same.
No, that's true. Both for the processes, and we think that's because the deposition of organic material is so variable along the trenches. So when we move along, you mentioned before you have these mudslides into the trenches. They form a given habitat, but then you move out of it or form a mudslide that has been there. In various places, you have small parcels of material that settle from the surface ocean down in the trenches, and they create a patchiness at the seabed that's extreme, depending on how much food has reached different locations. And one thing that's really taken us by surprise is how diverse the microbial communities are down there as well. Originally, we thought we would find sort of few specialists that's really adapted to this extreme pressure and perform very well at these conditions. But that was not the case. What we found was actually a huge diversity of microbes that were adapted to these conditions, these extreme conditions. But it seems like that for microbes, bacteria, for instance, it's very easy to adapt to these extreme pressures and temperatures. We don't quite yet understand how they are doing that. We have some theories, but it was really a revelation for us when we saw this huge diversity of very many different bacteria in the deep trenches rather than specialists, a few specialists that was adapted to the conditions.
Okay, a massive diversity, but of generalists or ones that can adapt to the conditions. So should we get into the microbial community? I know it gets complicated quite fast, but if we sort of render them down to their jobs, what are you finding?
Yeah. So what we are finding is that we have this huge variety of microbes that are able to do very many different processes. We're talking about dozens of different chemical processes they can facilitate. But when we look into their genomes, we sort of take out the DNA and we sequence them and look at them. They have very many different things they can do. They are generalists, as you say. They can sort of switch from one process to another process if that's convenient, means if the environment is changing. But we also see that they have ancestors that are very similar in the shallow water environments. So it must have happened very many times that microbes have been seeded into the deep ocean, to the deep trenches, and then these microbes have each adapted to the extreme conditions there. It's not like there's been a few that made it down there and then they colonized the
out.
Exactly. That's not the case. You have a constant.
So everyone came along,
and they keep coming. So that's also the fascinating thing. They keep coming, and they are relatively quickly in adapting to the extreme conditions down there.
Right. So strains that we know from shallower water, this isn't evolutionary time. They are coming down, and they can switch on or acquire certain genes that make them pressure adapted. At the sort of generational level. That's incredible.
Yeah. And one thing we think that's an explanation for this is that viruses are very important in sort of shuffling these genes around. We're used to looking at viruses as harmful organisms. We get sick from them, and so do bacteria, and they kill a lot of bacteria every day in the ocean. But what the viruses do is that they insert special genes in the bacteria to take over the bacteria and do what they want them to do. But once in a while, they also insert genes that actually makes the bacteria even more efficient to work under those conditions. And that goes much faster than to spread a gene that's beneficial to the community than classical evolution, where you have mutations that sort of inherited by the
generational. Isn't it called horizontal gene transfer or something like that?
Yeah, exactly. That's what we think is driving this. So we think we should think about viruses as an important component of how the microbes in the deep ocean functions by spreading beneficial genes among the bacteria. And that makes them so efficient to degrade organics down at these extreme conditions.
Wow. So you're kind of greeted in the deep sea by a virus that upgrades you to high pressure tolerance. Yeah. This feels like a computer game. This feels like when you get the upgrade and now, okay, I live in a trench now. I used to be on a rocky shore, but okay.
That's what we think is one of the tricks, at least the microbes can be doing.
They've got a bit of a Swiss Army knife of different modes of life that they can switch on and turn off as all microbial stuff blows me away because you get at the real fuzzy edges of life. It's hard to call them species when they're all sort of blending and exchanging genetic information and popping in and disappearing. It's hard to sort of keep track of them.
But they are so important. I mean, they are so important in driving all of these element cycles and these, what we talked about, the carbon monomerization, the nutrient remobilization.
Yeah, crucial. We wouldn't be here without them, including the ones in our own bodies, actually. They do a lot of bioengineering for us.
Yeah.
You showed me some of your work on marine snow. Is that published? Are you able to talk about that?
Yeah.
I just thought it was very cool, the resuspension chambers. Was marine snow a possible vector for the microbes getting down into the trenches? Because little nutrient packets they hop onto at the surface and then ride all the way down?
Yeah. We definitely think that's an important thing. So in the surface ocean, when you produce all of this organic goo or organic material that agglutinates or forms small aggregates, which we call marine snow, that starts sinking through the ocean and actually feed deeper part of the ocean gradually as it's moving down through the ocean. On that way, of course, some of the organic material is turned over. The communities are changing as it's sinking, and ultimately it makes it into the deep ocean. So that is a vector carrying microbes from the surface ocean into the deep ocean, but also a vector to carry other material from the surface ocean, including organic material, down at great depth. And one thing that we found out was that, of course, when the marine snow particle is formed at the surface, it's colonized mainly by microbes at the surface ocean. But what happens is that as this marine snow particle is sinking down, the pressure is increasing, and that actually inhibits, in the beginning, these microbes degrading the organic material. And that means the undigested organic material make it much, much deeper in the ocean than we thought before. Because what people have been doing before was to capture these marine snow particles, take them up on the ship, and measure how fast they decay. But they decay much faster on the ship than they do while sinking because the pressure inhibits the original inhabitants of each of these marine snow particles. So that's why we think that much more organic material make it down to great depth.
And you had some great experiments of marine snow tumbling under pressure conditions, and you've got some very cool tech in your lab. You've always been driving the forefronts of the technology. I think both of our groups really were the reason we were doing things that no one else had done was because we were building the tech that no one else had used, and it was always hand in hand with technology.
Yeah, that's true. It's very important. It is a technology-driven science, actually, studying the deep sea. It's enabling us to answer more and more questions, developing these technologies. And the pressure tank you're referring to here for the marine snow particle is no exception. I mean, we have these big tanks here that have a volume of about 12 liters, the big ones we have. And inside those, we have all of these marine snow particles, which we're making in the lab. And we can put in oxygen sensors in each of these snow particles. And while they're sinking, and we keep them sinking by the whole pressure tank is moving, rotating, and at the same time, we're increasing the pressure, simulating that it's sinking. And then we can measure processes directly in each of these marine snow particles. So it's very difficult to capture one snow particle out in the real ocean and studying it without touching it. But we can do it in the lab by these pressure tanks.
Even though we're obviously only on the beginning of figuring this all out, how are things looking for the future? I keep hearing ideas to sink carbon into the deep sea as a way of sort of sequestering carbon. But what is that going to do to these communities? Is that going to shift them in a certain way? Is it not going to work the way we think? Because it's not just locked away, it's food, and something's going to respire it.
Yeah, exactly. I'm not a big fan of these ideas of just dumping things into the ocean and think that will solve the problem.
It's not worked out well in the past. We've not done well.
No,
we're not very good at foresight.
And even just doing the math of calculating how much could we dump compared to how much fossil fuel we are burning, it would be such huge amount of organic carbon we would have to sink into the deep ocean. And of course, that will have environmental implications in the deep ocean. And as you also hinted to, of course, these organics will be overturned and mineralized and liberated as CO2. And they might be locked away for a while until ocean mixing is sort of bringing it back to the surface, but ultimately it will, depending on where it's happening. The deep sea is really, if it's seeded with organic material, it is really efficient in turning over that organic material. It's not just disappearing if you dump it into the ocean.
The sort of abiotic, sterile, okay, there's a few brittle stars down there idea of it doesn't really hold up anymore, especially not in your field of work where just the very sediment is alive and doing one of the crucial draws of this planet. So even if we did get it down there, it's not going to stay down there, or maybe not in the way that we expect.
One other example of how well connected actually these trench systems are to processes either in the shallow water or in the surface ocean is that we find all of these pollutants deep down in the trenches.
So, we didn't even touch on this.
So we have all these organic pollutants, PVC and PPC, produced by humans for very industrial purposes, and also heavy metals. And we find them really concentrated down in the deep trenches, showing that we have an important, efficient transport of these materials into the deep trenches, as well as the organic carbon. Also, the pollutants make it down there and actually accumulates in these systems at levels that's mind-blowing compared to what we expected, that these trenches were almost untouched by human impact. But they are not at all.
Yeah, even on the macro scale, it's unusual to not find a plastic bag or a beer bottle or something down there.
One good example of that, which was also a revelation for us, was that right after the tsunami, I think we can all remember in 2011, that hit east of Japan and also caused the Fukushima nuclear power plant to melt down and release a lot of waste into the environment. We went to the Japan trench 4 months after that incident to see what had happened in the Japan trench. And we could sort of see a lot of depositions of organic material down at the trench because the tsunami was caused by an earthquake that sort of destabilized the rims of the trench and thereby led into huge mudslides into the trench. But what we also found was waste from the Fukushima nuclear power plant. And that means that there was such an efficient transport of these radioactive wastes into the trench that we found them down in one of the deepest points in that region of the world, down the trench 4 months later. And that shows us how well connected these environments actually are to processes, both in the coastal zone and in this case even at land when a tsunami hits, and can transport material down in these trenches quite efficiently. They are not isolated, locked away environments. They are an active component of the global ocean.
As we look to the future, other issues that are mainly our fault, is climate change likely to shift these communities, or are they too diverse to even estimate what the future might hold with them? We're still figuring out how they work right now.
Yeah, they will certainly be affected. So what we can see is that when we go into different trench systems, they are very, very different. The communities and each of the trenches, when we talk about microbes at least, are very, very different. And that's because the loading of organic material from the surface ocean is different. And that means we have a very straight correlation between how much is the surface ocean production, which is mainly driven by the climate conditions, and what activities are happening deep down, 10 kilometers down in the trench. So there's a clear relation there. So that means if climate is changing the surface ocean production, it will quickly translate into how much food is making it down to the trenches. If production is declining at the surface ocean due to climate change, then we have less food in there. Or opposite, of course, if the production is increasing, we stimulate deposition of material and thereby changing the communities that are down there and all the processes that are happening in the sediments. So they are very much responsive to climate change in the surface ocean.
I know it is not directly Hadal Trench related, but the same sort of microbial processes are going to be impacted by future plans at deep sea mining.
Yes, I think that's one of the difficult dilemmas deep sea biologists, but also the industry is considering mining these manganese nodules that are spread around many areas in the deep ocean. We need these rare earth elements for our green transition here on the planet to at least partly try to fight the ongoing global climate change. On the other hand, it's very, very difficult to envision us harvesting all of these nodules without affecting the environment down there, and we certainly will. So I think it's a difficult dilemma. Should we continue just harvest them on land, as we are doing now, demolishing very many environments on land, becoming rarer and rarer, or should we consider to start harvesting in some areas of the deep ocean? And I think when I say we, I mean the scientists, the deep sea biologists, need to come together with the industry, find ways of where we can really test what is the impact of these mining efforts and how can we sort of do it most manageable, where we have least impact on the systems. And I think we're still moving along that path. And I think it's important we take our time to develop sort of the most sustainable way of harvesting these nodule environments before just jumping into doing it. But on the other hand, I also think it's too difficult to say we don't touch them. We just leave the deep sea, which is 60% of Earth, untouched while we are mining in the rainforest and destroying that. It is a tough dilemma.
Yeah, it's a tricky one. I spend a lot of time thinking about it, but I'm not sure I've reached conclusions. I think we need to show willing in a few other areas as well. I'd like to see our recycling get really, really hot so that, okay, we need more of these elements in circulation, but I need to see that we're good at keeping them in circulation. I feel that maybe certain lobbies would like us to keep acquiring new things rather than reusing what we have.
Yeah, I completely agree. Of course, that's a resource that we're not really tapping into when we're just dumping things and then mining new resources instead. Yeah,
that can't be better, right?
No,
it can't be easier than just getting it out again at the end.
But I mean, it's also naive. We as scientists don't interfere in that discussion. We need to do. I mean, it's our obligation, I think, to sort of give our qualified opinions about what to do and what not to do in these situations.
We usually end on a fun one, which is, what's the best party you've ever been to?
The best party?
Yeah.
Whoa.
We've had I know I should have warned you for this one because I don't think I could remember off the top of my head, but we've shared a few. We've been at sea. There's been some Kaylee dancing on a German ship in South America, I remember.
Certainly been some fantastic parties on board ships at the end of expeditions. People have worked so hard for so long, and they are all, in one way, exhausted, but they are also fired up by all the new discoveries they have done, and they are so excited looking at that, and that gives a special energy. So it doesn't take much to create a party on board and give a really great feeling on board. This teamwork thing also surfaces by the end of the journey. I think it's well deserved for anyone on board that has worked so hard for so long. So I don't know if I have a particular one, but I have certainly many times enjoyed, together with good colleagues, fantastic parties at the end of expeditions.
It's the creativity as well. I've seen people disappear and make costumes out of Petri dishes and pipette tips and things like that.
Yeah.
It's a kind of mania, but it's a good one. It's a good party atmosphere. Thanks so much for coming on and having a chat with us, Ronnie. It's a tiny and huge subject, and I have a real hard time getting my brain around it. And not just in this field, but in a few other fields, we're starting to get an idea of just how important the microbiome is, how flexible it is, how collaborative it is, if that makes sense. It isn't all predator-prey. Viruses seem to occupy a very strange area where they can be beneficial and they're shunting important genes horizontally. All the edges get really blurred. I find this a really interesting area to think about, but I lose sight of it so quickly.
And there's still a lot to discover out there. It's only the tip of the iceberg that we really understand about the microbial communities in the deep and how the deep trenches functions.
Thanks for talking with us.
You're welcome.
Life's getting really weird at that scale. I find it really hard to get my head around that.
Lucky you're not a microbiologist, Dan, isn't it?
It's good. I'm going to keep it that way.
I always had a rule in my career that I don't understand anything that I cannot drill a hole through.
It's a good marker. It's a good
That's
barret.
the size class. If I can pop a hole through it, even if it's a 1 millimeter diameter drill bit, that's fine.
Yeah.
But anything that I can't do that, then I just don't seem to understand it.
As long as you can hammer it to a board.
Yeah.
That's senior right. That's a fine standard.
I can blag my way through it in the same ways I do with all these people I've employed over the years to do genetics. I say, sure. I still don't understand what goes on in those little tubes when they're doing this, that, and that. I know the question to give them to answer, and I understand the answer to the question. I just don't understand the bit in the middle. I just can't get my head around it. So I can't drill a hole through any of this. It's all going on at a scale I don't understand. So I'm out. So I've got a really good idea. Get someone else in to do the lab work and then come back and tell me what the answer to my question is. That's how we work. And it's very interesting and I love it, but I can't be an expert in everything.
To round off this episode, I touch base with a deep sea celebrity, but I won't spoil the punchline. Soon become apparent why I wanted to speak to this person. We are on a small liveaboard off Norfolk Island, and I'm here with Kieran Parkinson from the Australian Museum, Sydney. We've been collecting cryptic fishes off Norfolk Island, but we're going to take a little sidebar because you've come up quite a lot in the podcast and I got to meet you in person. So why might you be relevant to the Deep Sea podcast?
Well, relevant perhaps in that I was the person that took the photograph of the blobfish. And Tom here seems quite excited about that.
I am very excited.
We're going to have a little chat.
Okay, talk us through the day. Because it's about 22 years ago, 21 years ago?
2003. It's 3rd of June, 2003. So that's coming up to 22 years ago. I was on board the Tangaroa and I was doing the 2 p.m. to 2 a.m. shift. We were getting an amazing amount of stuff coming up from down deep. And on this particular trawl, everybody had been out on deck, collected specimens they'd been identified, and I was doing all the photography, so I got to see all the really, really cool stuff. And the blobfish just happened to be one of those really, really cool fish.
And it was right at the end, wasn't it? It was like the Or did you come back to it? Because the iconic picture was kind of a little like right at the end of a processing session, wasn't it?
Yeah. So everything that came up to me, I was photographing, and this guy or girl came up towards the end, and we did the usual scientific photograph where we have the head pointing to the left, tail to the right, color chart in there,
Scale bar and label and all the stuff we're meant to do.
Specimen. And it was, you've been working 12-hour shifts for a large number of days, and it just looked kind of funny when we set it back up again, and we're like, oh yeah, let's take a photo like that. And that's pretty much how that iconic photograph was taken.
And I think for me, it was like the first meme, really early days of the internet, but it's hung around for a while. Like, I don't know if somebody found the report or you gave a few talks initially and it made it into the talks.
Honestly, I don't know.
It was years before it appeared and then went huge.
Yeah, so 2003 was the year the photograph was taken. I had to create a story photo slideshow at the end of the, it was called the Norfans expedition that we were on. And that was shown to a number of people. I don't really recall what happened to it after that. But everything went quiet, and then all of a sudden it was on, I think it was on TV on the Gruen transfer or some TV show.
That was when
in Australia. And then it went berserko. And I still get requests to use the image all the time. Hasn't stopped for 22 years.
So still regularly getting emails.
Yeah.
Are you allowed to share some of the unusual ones you've gotten? Because it's...
Well,
a lot of people see a lot of different things in that fish. They
do.
Project.
I mean, most people know that it's been voted the world's ugliest animal. I would dispute that. I think it's quite charismatic. And I think in some way, thinking about how it lives deep down the ocean, you've got to be pretty excited about how it's adapted to the way it lives. And that's what its skin looks like when it comes up out. We've dragged it up from 1,500 meters. Well, you know what? It's okay.
And that's on us. That's what we've done to it. We can't put it through these forces and then decide it looks ugly. It's like
That's right.
It's been through a lot.
Yeah. It has been through a lot. Yeah, look, I get a lot of requests for using the image for a whole lot of things. Some of my favorite ones were for a CD cover for a musician.
Nice.
Political party in the US. And I have had some interesting ones where people have wanted to use it for all sorts of weird and wonderful things, mostly science, mostly education. Sometimes it's for church groups to show how wondrous God is. You know what? That's okay. The word gets out there that there's these really cool
great
pictures
fiction.
out there. I'm okay with that. So yeah, there's been some very interesting ones. I do get a request probably once every couple of weeks.
Wow.
Yeah.
Wow. And we started ranting on about it because so many people have lost the origin of that image and that your credit very rarely gets there. So how many are not getting to you?
Oh, probably heaps. And there's probably heaps that people try to email me or perhaps it bounces. I don't know. But yeah, I do regularly, probably once every 2 weeks, get another new email saying, can we please use the image for said purpose? So it's kind of funny.
And we've just had a little mooch online now and plenty of people are using it without permission because it's a whole brand. It's a whole merch.
That poor fish has been used and abused. There is T-shirts, there is phone cases, there is stickers, there is Duna covers, there is slippers.
Yes, Andrea has a pair of slippers.
Soft toys.
Yeah. Yes.
Tote bags. I have a tote bag.
Oh, good.
Yeah.
Oh.
It's nice. But there's a lot of stuff out there, I know. Poor blobfish.
Famous blobfish. Celebrity blobfish.
Yes. And a lot of people are really interested. I meet a lot of people who are teachers, and when they find out that I took the photograph, they're like, oh my gosh, my kids love that photograph in class. We talk about it. It starts conversations about science and animals and stuff. So that's pretty cool to hear, actually.
Yeah.
So,
we always refer to it as like one of the ambassadors for the deep sea, and that it's not, I don't know, people relate to it so well. It's so charismatic. People project a lot onto it. So it's good to have a deep sea fish with a bit of personality that isn't just alien monster, toothy.
Indeed.
Look how horrible this thing is.
Yeah, it would be nice if we knew a bit more about the fish, if we knew a bit more about their habitat and all the rest of it, lifestyle, longevity. One day we'll have the technology to be down there and we'll learn more. So
yeah, there's very little footage of the blob sculpins, like in situ. There's slightly more now, but yeah, we still don't know much about how they hang out.
No, we know that they protect their nest.
Nice. Oh,
We do know that.
blob's a good parent. And do we know if it's the male or female?
We don't. No, we did CT scan the specimen to see if we could figure out if there was any obvious structures, but I can confirm that there was no obvious
It's
structure.
blob all the way through.
Yeah.
Well, it's been a really long day, but thank you for having a quick little chat because I knew I wanted to do this as soon as I got on the boat. So thank you for
Thank you for having me.
Completing this story, because it started with a blog, and then me and Andrew were on the Tangaroa and we were talking about it because we caught a blobfish, and now it feels like it's come full circle and we've gotten to the source.
My pleasure. Thank you for having me.
And that concludes this episode of the Deep Sea Podcast. If you'd like to... Oh, actually, I do have an announcement. In the show notes to this one. So I usually say the email address, and the email address will be in there if you want to write to us. But Megan has been clever and has set up an answer phone for us.
Ooh.
So you can click on a link and you can record us a message if you don't fancy it. Yeah, if you don't fancy writing an email. So the Deep Sea Podcast has an answer phone now.
Can I lose stuff on it?
Yeah.
Oh, give me the number.
How long until I get an email to say it's full?
I've got a few things to get off my chest. I feel like that's the only thing that'll listen to me now.
We've got an answer phone now, so I'd really like to get some messages from folks. So until the next episode, we'll deep see you next time, and we'll miss you already.
Do you remember you put a Barocca into vodka and called it a Barocca?
Yeah.
Healthy vodka. Remember
Good
that?
times, yeah. I forgot about Barocca, because I'll be honest with you, that's not the first or last time I did that. It's kind of my go-to.
I believe your phrase after drinking several Baroccas was healthy smashed. Yeah.